Okay, so picture this. You're a scientist in a lab. You've got this tiny piece of a meteorite, something that's traveled across the solar system for billions of years. You heat it up, expecting to see it, well, rust. But then you look under the microscope, and what you see is something way weirder, something that almost looks alive. Let's get into what they found.
So, can a piece of metal actually grow whiskers? I mean, it sounds like something straight out of sci-fi, right? A chunk of solid, totally lifeless metal just sprouting these tiny hair-like things? Well, it turns out, under just the right conditions, the answer is a big, resounding yes.
And you can almost feel the surprise in the scientists' own notes. They wrote, and I'm quoting here, that blades, needles, and whiskers of various morphologies were discovered. We're not talking about just some random crystals here. No, these were distinct, super thin, hair-like structures, some of them less than a micron thick, literally growing right out of the metal itself.
All right, so what exactly are we looking at here? This isn't something that happened out in the cold vacuum of space. Nope, this is a story about one very special meteorite and one very clever experiment. The star of our show is the Gibeon meteorite, this famous iron meteorite from Namibia. But here's the really important part. Scientists C.W. Visser and Bruce Fegley Jr. didn't just find these whiskers on the meteorite. That's not what happened. They actually grew them in their lab by carefully heating up tiny filings from it. Okay, so we've got the what and the where. The next big question is, how? How on earth did they make this happen? Well, it all comes down to a really controlled experiment in oxidation, which is, just a fancy scientific way of saying they made it rust.
And their process was super methodical. First, they took the meteorite and made these little filings and foils. Then, they heated those samples up in dry air, using a whole range of really high temperatures. And as they did this, they kept weighing the samples to track exactly how much rust, or oxide, was forming. But the magic moment, the real discovery, came when they put the results under some seriously powerful microscopes to see what they'd actually made.
So after all that careful heating and weighing, what did they find? Well, the rust that formed was nothing like what you'd see on an old bike. Oh no, this was something way more complex, and honestly, pretty beautifully structured. Instead of just getting one single uniform layer of rust, the meteorite formed what's called a duplex oxide layer. The easiest way to think about it is like a little sandwich. You've got the original unrusted meteorite metal on the bottom, and then two totally distinct layers of oxide stacked right on top.
And this isn't just any sandwich. It has two very specific layers. The outer layer, the one exposed to the air, was made of something called hematite. And the inner layer, sitting right on top of the metal, was a magnetite spinel. Now here's the crucial part. Those weird whiskers we saw at the beginning, they grew directly out of that outer hematite layer. So let's get specific. Hematite, or alpha Fe2O3 if you want to get technical, is the key ingredient here. The researchers even noted that the needles and whiskers had this reddish color, which is a total giveaway for hematite. So what we're looking at are basically tiny crystalline whiskers made of a very particular kind of rust.
But, this just brings up another question, right? Why did it grow this way? Why these two layers? And why the heck did it grow whiskers? Your average piece of iron just doesn't do this. There had to be something special, something different about the meteorite itself.
And you guessed it, there was. The Gibeon meteorite isn't just pure iron. It's an iron-nickel alloy, and it turns out that little bit of nickel completely changed the game. It was the secret ingredient that controlled the entire oxidation process.
So check this out. This is really the core of the discovery. As the iron atoms were getting pulled away from the alloy to form those rust layers, the nickel got left behind. It was basically pushed down, getting incredibly concentrated right at the boundary between the metal and the oxide layer. We're talking up to 65% nickel in that tiny, tiny zone. That's a huge increase. And this massive concentration of nickel had three major effects. First, it kind of acted like a shield, slowing the whole rusting process way down. Second, it stopped a different kind of iron oxide called wüstite from forming, which is something you'd normally expect to see on pure iron. And third, some of that nickel actually got incorporated into that inner magnetite layer, changing its chemical makeup. Okay, so we know what the whiskers are made of, and we know that nickel created the perfect chemical conditions for them. But how did they physically grow into these long, thin needles? Well, the scientists proposed a theory based on earlier work, and it's called the screw dislocation mechanism. Now, I know that sounds super complex, but the idea behind it is actually pretty cool. Just imagine these tiny, invisible flaws, defects, running through the crystal structure of the metal. The theory is that these defects can act like microscopic straws, creating a little channel that sucks up iron atoms from the base of the whisker and transports them all the way to the growing tip. It's like a conveyor belt, continuously feeding the whisker's growth outward.
All right, now this is the part where a small lab experiment about microscopic rust whiskers suddenly gets really, really big. Because this isn't just some weird little curiosity. It might actually give us clues about the very beginnings of our solar system. See, the researchers wrapped up their paper by saying their findings have possible implications for nebular chemistry. Now, what does that mean? Well, nebular chemistry refers to all the chemical reactions that were happening in the solar nebula, that giant swirling cloud of gas and dust that eventually collapsed to form our sun and all the planets, something like 4.5 billion years ago.
And that's the truly mind-bending takeaway here. Think about it. Could the way a tiny piece of meteorite rusts in a lab actually teach us how planets were born? By understanding how an iron-nickel alloy, which was super common in the early solar system, behaves under heat and oxygen, we can build better models of the chemical processes that turned that ancient dust cloud into the worlds we see today. It just goes to show how even the smallest, weirdest little discovery can echo the grandest stories of the cosmos.